Okay, did everybody get their Lab 1 uploaded okay? Anybody have any issues getting it turned in? Okay, well, from Lab 1, I put a list on the board of things you should know after completing Lab 1. You should understand what we mean by the term logic continuity and how it applies to programming the rungs. You should know how to build and understand the logic of a start-stop control using a Sylin circuit or latch. You should understand how each instruction that you drag onto a rung, understand how each one maps to the data table. Remember, the data table is called the input image table or output image table in textbooks. And then your simulation software is referred to as a data table. But understand how each instruction maps to a certain bit position in the input or output image table, the data table. Those are actually, you're actually viewing what's in the register, and each cell of the register maps to a certain terminal on the input module or the output module. And then you should know how to view the contents of the data table. The data table actually stores binary information, but using the radix function, you can control how you excuse me, you can control how you view the data. You can view it in hex, you can view it in octal, you can view it in decimal, but it's stored in binary. So those are the main objectives. And then going through the tutorial and just kind of playing around with the simulation software, you should understand that every time you make a change in your program, you have to download that program to the PLC. You have to re-download it. Now, on the first day of class, I mentioned the fact that if you look at a PLC in the factory, it looks like a box sitting on the wall. Even though it's a computer, you might not recognize it at first as a computer because often you don't need a programming device. When you program a PLC, the actual programming device often has memory in it. And so when you actually write the program, that program is held in memory in the programming device. And then you can hit a download button or enter button, and then it's moved from the memory of the programming device to the CPU. And so your simulation software, there was a download button you had to hit every time to to mimic that. So these are the main ideas, main objectives you should have gotten from the Lab 1, and we'll keep building on this in the next lab. So I had scheduled the exam for today, and I got to looking at Canvas, and I built this course and kind of redid some things last semester, and I actually had the exam further out. So I canceled the exam. I'll give you the new due date. It'll be a couple weeks from today. And I'll give you a list of the study points, again, what to study for the exam. I don't think that's going to change too much. But I am going to give you a quiz 6. I need to go in and make some adjustments to it. So what I'll do, what I said before is I was going to start the Friday quizzes during the lab period now, but I'm going to wait, just give you that quiz over the weekend. I got to go in and make some adjustments to the quiz to edit it, and then after that I'll give the quizzes on Fridays. So I'll let you know the new date for exam 1, and we'll just stay on course, keep everything on course. So I want to go into this PowerPoint. Yeah, you got a question? Yeah, I can hear you.
Do you mind if you set the lab 1 due date to always be like at midnight?
Yeah, I can do that. I can do that. And I actually did that. Somebody had some kind of issue, so I did that for Lab 1. That's why I asked if anybody had any issues. But from now on, if that works better for you guys, I'll have them do it midnight on the Friday. If that
Yeah,
works.
because I feel like if we have any question for lab, it would help. Like we go into like class today and we ask you, that would probably help some more.
Okay, that's a fair. I think that's a great idea. Thank you.
Yeah,
So,
because I was rushing a lot of it to get it to like the due date at 9.
okay.
So I mean, hopefully I think I know what I was doing, but I think like for majority, probably like asking you questions and stuff would benefits more.
Okay, I think that's a good idea. So we'll do that. Now, I did extend did extend it. I didn't announce it, but I did extend this lab to midnight. And
Yeah.
if you gotta go in and make some adjustments, you can upload it up to 2 times, so you can always go in and do that. But yeah, I think that's a great idea, and I'll do that from now on. I'll make it do on midnight.
Okay.
Thank you for that.
I appreciate that. Thank you.
All right, anybody else? Okay, well, let's get into the lecture, and then if you have any questions, I'll have time. We'll be done before our, the normal class time. We'll have time at the end. So let me go through this, and I kind of held this one back. This is we already talked about programming the PLC, but this one, I think, after you went through Lab 1, then what I'm going to say, what I'm going to refer to in this PowerPoint is going to make a lot more sense, and it should deepen your understanding of how the PLC functions, understanding how the PLC views programs and how it behaves, how it interacts with the input-output modules and the data table. It helps you to program it better. So this is going to be this should be a really good PowerPoint for you to kind of think about what you did in Lab 1 and kind of reflect on what we're talking about. So you know by now that each input and output in the PLC is you connect to a screw terminal on the input or output module. Each screw terminal has an address, and you can map a bit position in the input or output image table, that is the data table, to a screw terminal using an address. And you guys done that. You drag instructions to your ROM, and you gave it an address, and each one of those addresses point directly to a cell in the input or output image table. So that should be familiar to you. Now, there's this term processor memory organization that's, you don't really need to understand it to program, but it kind of helps, as I said, deepen your understanding of what's going on in the machine, which in turn I think makes you a better programmer. So,
Quick question: when can we find the PowerPoint?
the PowerPoint, I sent that out when I made the announcement. I attached it as a link. So however you guys view your announcements in Canvas, it should be linked to that. I will, however, I'll put it up on your Canvas. I didn't get a chance to do it last night, but you should have a copy of it. I don't know when I make an announcement if it goes to your email. It's probably in your email. But I linked it to the announcement that I made yesterday.
Yeah, I found it.
Yeah. So
sorry if I interrupt you.
No, you're fine. That's okay. Okay, so so this idea of memory organization helps you, just kind of deepens your understanding of what's going on behind the scenes, and in turn, I think that makes you a better programmer. So different PLC manufacturers organize memory in different ways, but pretty much what I'm going to say about memory organization is kind of generic, so this will work for any PLC or any PLC manufacturer. Now, your simulation software is modeled after a company by the name of Allen Bradley. It's the SLC 500, and this one is the Allen Bradley PC2 memory organization. But for purposes of this class, if I talk about or ask about memory organization, and on the quiz or exam or homework, this slide right here is what I'm referring to. So remember, memory is organized in different ways depending on what PLC manufacturer you're talking about and what model PLC we're discussing. But this is kind of a generic way to view memory and how the programs are held in memory that I think will work for any PLC. So if you have a printout, I know I didn't put the PowerPoint where I should have. I attached it to your email, but you do want to mark this slide right here. If you don't have the actual handout, just maybe write the title of the slide. You want to remember this diagram. So basically, you have three portions of memory, and we'll go in and we'll talk about what these parts are. But the data table part is exactly what you think it is. That's that input-output image table or the data table that you guys work with in Lab 1. So there's a space in memory for that. That data table does a specific thing, and you know what it does. It stores those zeros and ones, which affects the output or inputs. Then there's the part that you control, the program. You write the program, that's stored in a different section of memory. So the part where it says user program, when you make that ladder rung and you upload it or download it to the PLC, it goes into this section of memory. And then there's this section right here that you do not have access to. We just call it housekeeping memory. But really what that does is there's things behind the scene that the PLC is doing, or really any computer is doing, that you're not aware of. So think of it like that. Think about it like, when you how can I think about it like when you breathe, you don't have to think to breathe, right? That's kind of automatic. That's kind of runs in the background of your brain, breathing and blinking your eyes and stuff. You don't have to think about everything. It kind of runs in the background of your mind. Well, this is exactly the same way. And with PLCs, or actually with any digital device, you have things running in the background that the user is not aware of. And so that's what we mean by housekeeping memory. And so you don't have access to that, and just know it exists, but it's really not important for what we're going to do in this class. What's important is the data table section and the user program section. So we'll go into this a little bit more detail, but you should be aware of it after that first lab. Here's a more detailed memory map, and I don't really care. This is not an important slide. I think the point is to understand that each section of the memory has an address. Just like the input-output terminals have an address in the data table, each section of memory has an address because you gotta be able to refer to that section of memory to either read the contents or write to the contents of memory. And so these are different areas of memory. So there's one for this processor work area. We'll talk about timers and counters, but there's a different section for that. And so that's more of like a more detailed version or a higher resolution of this one. But this is the one I want you to remember. Just if you can remember that for the exam, you'll be in good shape. And just understand that we can drill down if we wanted to and go into more detail and say exactly where different portions of memory store. And that's the point of this slide. But the user program section is the part that, this is the part where you have access to, not directly to the memory, but when you write a program, when you put together that ladder rung, the ladder logic, it's stored in this section. And so this section right here, this is the one that probably requires the most memory. The longer your program, the more of this memory you're going to use. So I'm not going to read this point by point, but basically it's where you store the program, where your program is stored, and understand that this part of the PLC, this section of memory, is probably, I won't say the most important, but it's very important, because if you don't have enough memory, you have a really long ladder rung, and you can imagine the issue that might cause. So this is important. Most of the memory is used for storage of your program. And then there's this other section. We refer to this as the data table, and you work with the data table in Lab 1. But there's this other section, the data table, and you know what that does. In textbooks, we refer to the data table as an image table. And what that does, there's two image tables. There's an input image table and there's an output image table. So it stores the state of the switches connected to the screw terminals on the input module or the output module. Sources whether the output should be on or off depending on your program. So you looked at that. Now what you didn't see yet in Lab 1, you looked at the portion of the data table that only stores status bits. And what I mean by status bit, you had switches hooked to your input module on Lab 1 or buttons, and if that switch or button was open or closed, depending on the state of that switch or button, it would put a 1 or 0 in a cell in the data table, in the input image table. Well, the input image table, there's also a section of it that stores basically data for counters and data for timers, and you can view that data also. And that's coming in another lab, so I won't worry about it right now. But just understand that what you saw in Lab 1, it actually is a little bit more involved than that. You you can adjust that table so you're looking at the contents of a timer or contents of a counter. And you can imagine that if I have a timer or counter, that won't be a bit-oriented storage for data. It's a bit more of a word-oriented storage for data. So we'll get to that at a later date. So this is the user program section where you store your program, and then this data table section where the input output image table or data table is stored. Now you want to make sure you understand a couple things here. Right here, it talks about status data and numbers or codes. You should know the difference for the exam between, or I don't know if it's exam one, but for some exam or at some point, the difference between status data and numbers or codes. Status data is what you think it is. If a switch is, the status of a switch or button is open, then in that particular cell that it's mapped to, that will be stored as 0. If that particular button or switch is closed, the status of the switch, open or closed, is represented by a binary 1 or 0, and so that can be recorded in the data table. Or the data table can store numbers or codes. Now remember, a number has place value. A code is just a sequence of bits. So we talked about that, I think, like week 2 in the semester. We talked about the difference between numbers and codes and that kind of thing. So that's what the data table section of memory can do. I guess the one that here that I circled is important, and probably this one to understand. But you've seen that if you went through Lab 1. So this is old news right here. Now, when you create a rung, in the background, your PLC automatically creates something called a processor file. And that processor file consists of two things, two sections, two categories. The processor file consists of program files and data files. Program files and data files. And you don't really have to know this to program, but it kind of helps to understand what's going on in the background. Now, I have a reference here. Right here it says see handout, and I don't think I sent you that handout. I'll put that when I put this slide, when I put this PowerPoint up on your Canvas, I'll put this handout up there too. You can refer to that. But so just know that these exist, the program files and data files, and there'll be a certain part of, and maybe I'll bring the program up and I'll actually show you, you can actually view these files. And if you go to, you might have already, I don't know how much you played around with your simulation software, but if you know where you bring up the I/O simulator, the I/O simulator is on the left side of the screen of your simulation software. If you X out of that, you'll see these files behind the I/O simulation portion of your simulator, and you'll see these files. But I'll refer to these later on, so it's not a big deal. Now, this should make sense to you now. We connect a switch. This is all hardware. This input module is hardware. And then what you see right here, this is all inside of the machine. This is software. It's all virtual stuff. So what you did in the lab, you connected a switch or a button to a screw terminal. And then that screw terminal is mapped. This is like one row in the input image table. And through the address, this screw terminal is mapped to a certain cell in that input image table or data table. And if the switch is closed, then this will record a 1. If that switch or button is open, it will record a 0. Okay, so you can think of that kind of structured or stored in what we call a data file, or data table file. So we talked about the processor files, which is the data files, is where you hold basically copies of the input image tables or output image tables. Same with the output image table. So if after reading your program for a particular rung, if that rung has logic continuity, then the output, the last instruction on your rung, is mapped to a certain bit position in the output image table. and that is mapped to a certain screw terminal on the output module, and depending on the status of this bit, it'll either turn this, in this case, the light off or on. But again, that's stored in a data file called the output image table file. So you can think of the output and input image table as these files, and you can have more than one of these. You can have one for the input output modules, you can have one for timers, and all the other stuff that I talked about before. Now this next slide is important. So again, if you don't have the PowerPoint, just write the title of the slide down. This talks about the operating cycle. Now here is one area where PLCs differ from other digital devices. Remember, the PLCs differ in two ways. One way I told you about already. PLCs are bit oriented. Your cell phone, computers, other digital devices are byte oriented. And what I mean by that is the smallest piece of data you can access on your cell phone or on a computer is a byte, 8 bits. Letters, numbers are all represented as 8 bits. Pixels, 8 bits. In a PLC, you're looking at the specific state of a switch or button to see if it's open or closed. And in that case, you're controlling a specific bit. You're recording a 1 or a 0. Okay, so that's one difference between a PLC and other digital devices. But this slide right here shows another difference that's important. PLCs run in a continuous loop. They run in the loop. So if you had programming courses before, you probably know what a loop is. You can make a loop, all different kind of loops depending on the language. But the program just kind of runs in this loop, and there's the section of the loop or cycle called the I/O scan, where the input output is scanned. Actually, the inputs are scanned, and then there's the program scan. So the PLC is doing two things. It's looking at the inputs, the physical input, where you have the screw terminal connected to a button or switch, and it's looking to see, hey, is the switch or button connected to this particular screw terminal? Is it open or is it closed? And depending on if it's open or closed, it'll update the input or output image table. And then you got the part of the scan cycle where it's looking at your program that you wrote to see what you're supposed to do with those bits. And remember, the object is, if you want a certain thing to happen, certain logic to happen, you got to have logic continuity for each particular run. So this kind of scans through it in this loop. You want to remember, I believe I asked this on the exam, but this little relationship right here, you want to remember the picture or this. You'll see that again. So the operating cycle has a program scan part and then an input-output scan. Now here is kind of just talk about the way this happens. So first we're going to read the inputs, the physical inputs of the switches or sensors connected to the hardware, the input module. And then it looks at your program, and depending on how you wrote the program, when the program scans, if there's logic continuity, then what will happen is the output image table will be updated with a 1. If there's no logic continuity based on the logic that you wrote, then the output image table, if it was a 1, it will be changed to a 0. If it was already a 0 and that bit position stored for that run, then it will stay a 0 or will update to a 1 depending on your logic. And so this is probably a good slide to mark, just to kind of understand this in more detail, this one. So that kind of walks you through it. Now, okay, so again, this right here, what you see on the left and the right, all this is actual hardware. So this is the actual input module and the switch that you connected up, and this is the output module. So this is hardware, but everything in between here is inside the PLC. This is all virtual. This is all software. Now remember, in the processor memory, we got two parts of memory that you as a user can access. You can access, well, actually, you have direct access to this portion of memory. This is the user program portion. This is where your ladder information is stored. And then the data is stored right here in the data table, the input, output, image table. So what happens here is you have a switch here connected to the screw terminal of the input module, and that switch has an address. You have the program that you wrote, which has that same address, and that's what maps the screw terminal to this particular address and this address to a position in the input image table. And depending on the state of this switch, there'll be a 1 or 0 recorded. And actually, I can just kind of walk through this. There'll be a 1 or 0 recorded. I think this does it. Yeah, okay. So look at the switch to see if it's open or closed. Let me go back to this. I'm clicking through this too fast. Kind of lost my place here. Hold on a second. Something kind of got away from me. All right, so we're right here. And then we look at the switch to see if it's open or closed. Because the switch is closed, there's a 1 recorded, and that bit position is mapped to that address. So there's a 1, it's updated to a 1. Because you use this examine if closed, it wants to see a 1 in that cell that it's mapped to. So there's a 1 there, which makes this rung true. So the light bulb lights up over here, turned yellow. We can go back through the process where there's a 0 there, so that makes this command false. And as it scans around again, it turned the output off. I think the whole point of this is, if you go back to the slide where it talked about the operating cycle or the program scan, it takes time to do all of this stuff. It doesn't happen instantaneously. It takes time to do that. So that turns out to be kind of important. There's this PLC scan time that, and I'll talk about that. It's the last thing I'm going to talk about in this PowerPoint. So I'll tell you why that program time is important. This slide right here, I don't really care about. You can read this. I don't even know why I have it here. I'm not going to ask anything about the scan patterns. You got these scan, so you can read it. It might be interesting. But this right here is actually what I wanted to refer to. And I talked about the fact that for all this stuff to happen, the switch has to open and close, open or close. The processor has to read the status of that switch, whether it's open or closed, and then it has to store that binary information. The status of the switch is a 1 or a 0. It has to store that in the data table, and then it has to go and look at your program. All of that takes time. TIME takes time. So the idea of program scan time is really, really, really important. Now, I want you to mark this slide, and I want you to read it. I'm not going to read the whole thing to you, but I'll just kind of give you an overview of it. But read this in detail. Make sure you understand this. You'll see this again on an exam or a quiz. The idea is, since you understand that the PLC is running in this loop, it takes time to go through the loop. And so let's say that you have a switch that operates faster than the scan time. Here's a good example on the PowerPoint. If it takes 8 milliseconds for the CPU to scan a program, but you got this switch that's opening and closing every 4 seconds, every 4 milliseconds. If it takes 8 milliseconds for the PLC to go through that scan that we talked about, and you have some kind of switch opening and closing every 4 milliseconds, you can see the problem that might cause. You're probably gonna not update the input image table, or you're gonna lose some data. So if you have any kind of high-speed operation where this is a possibility, you have to be concerned with programs scan time. I would say under normal circumstances, mechanical switches move a lot slower than the PLC scan time. So it's usually not a problem. But if you have some kind of special application and you have some kind of high-speed application, then this could be an issue, and you would at that point want to be aware of scan time. So go ahead and mark this slide, read it, and make sure you understand the details of it. And if you have any questions, you can ask me about it later. I don't think it's anything. It's not rocket science or anything like that. Pretty easy to understand, but mark it and make it something you can study for your quiz or exam. Now, guys, I'm sorry I'm losing my voice. I can hardly talk. I don't know why. But that's really it for today. Anybody have any questions over the PowerPoint or general questions about the Lab 1 or anything in general? Any questions or comments?
I had a question.
Sure.
You mentioned like we're using Allen Bradley type PLC.
Well, your simulation software is modeled after Allen Bradley PLC. The model they call it SLC 500, but it's a SLC 500 Allen Bradley PLC. So
Okay.
Yeah. Do you use one at work?
No, at my previous co-op, the experience I had with PLC, we used Omron type PLC.
Okay, I'm not familiar. I'm familiar with Allen Bradley, Motorola, and then there's a couple Japanese brands, but I'm not familiar with that one. Did you get the program and play around with it?
Yeah, I didn't get to do too much hands-on stuff with it, but I kind of learned the ins and outs of how it works, and I was just wondering kind of what the difference is between different brands of PLC, I guess you would call it.
Yeah, so one difference is remember early on in the semester, I mentioned that I said that we talked about sizes of binary information. You got a bit, you got a byte, and then we said a word is machine dependent. We said for us in here, a word's going to be 16 bits. Well, the reason we said that is if you remember in your simulation software, in the I/O simulation portion of it, there were actually screw terminals numbered 0 through 15. So there was 16 screw terminals. So each row of the input image table has to have a storage place for a 0 or 1 for each screw terminal on the input image table, or each screw terminal on the input module and the output module. Because Allen Bradley, for the SLC 500, they have 16 screw terminals. You have some PLCs that would only have 8, so the word size for that particular model, that particular manufacturer, might be 8 bits. You have some that might have 64 screw terminals you can connect to. So the input image table will be that row would be a little bit bigger. So things like that would vary from one manufacturer to another. The word size and the operating cycle speed, all of that. That's based on the microprocessor. So but what we talk about in here, even though it's kind of pointed towards the SLC 500 Allen Bradley, should carry over to pretty much any PLC that you use, that you will come in contact with, when you guys graduate. Okay. So that's a good question. That's a really good question.
All right, thank you.
So guys, I actually, I'm done, but I actually was working, last week I worked with, and I'll show it to you. I have a little micro PLC here that has just 4 connections to it. And this thing, I'll show it to you if I think about it on camera next time. But then you can buy a PLC as small as a pack of cigarettes and have it control. And that's kind of basically if you have a garage door opener, what you basically have is a very simple PLC with certain functionalities. You don't have to make any adjustments because it's kind of a dedicated, device, but it has everything that the PLC would have, except you don't need to program it because it's already programmed. Any more questions or comments? That was a good question. Well, guys, I'll be posting up the next lab, and I got to go in and I got to make a few adjustments to it. I got to change a few things. I don't want to keep everything the same as I had in previous classes. But I'll be posting that, and I'll send out an announcement. And then if you have any issues or questions, I'll address those by text. And then that next lab, I don't know who that was that made the suggestion that we just make them do Friday midnight. That way, if you have some questions, you can ask. I think that's a good idea. So the next lab, I'll post it this weekend, and it will be due next Friday at midnight. And then I'll give you information about when exam 1 is going to happen. Guys, have a great rest of the day. Stay safe, and I will see you soon.